Good day, guys. So let's continue our discussion on tension members. So this time we look into the simple procedure on how to design it by giving you a step-by-step guide on how to deal with it. Although design procedures can be trial and error, direct trial and error, it is perhaps much more convenient if you can make use of a system of steps involved to come up with a good design process for you to be able to program it also later in your design worksheets such as Excel or MathCAD. So for the design procedure, this is how it goes. So we just look into getting a trial area from the criteria uh, based on either LRFD or ASD, but here the criteria was based on, of course, LRFD. So these two steps here is just a simple way of getting a feel of what the value of the area is using the yielding at the gross section and the fracturing at the next section. So this is a yielding failure, and this is a fractural failure. And then of course we have to choose from among the two, but before we do that, before we choose from that, we have to convert the area effective to another AG to compare it with the first. Okay, so you call this now your first AG, and you call this now the second AG, and from this you can choose the larger of the two that will satisfy both the requirements on serviceability and strength. Okay, so we choose the largest, and then we find the required R minimum for serviceability requirement. So this is now serviceability check. This is criteria for strength. Okay, and of course, after getting a feel of what the AGNR is, we can go to the table to select a section. If we want to be standard section, if not, we can use our own imagination to come up with a section. And then, of course, we have to detail the connection for the selected member and again check the design criteria. Of course, in the computational part, your step will be uh, will can be ended, no? Can be stopped right at this very point. So for problem T-6, we have a tension member with a specific length 5 feet 9 inches, and it is to resist service dead load of 18 kips and a service live load of 52 kips. We are asked to select a rectangular section, so this is just a plate, so it's still easy. So we have only a rectangular plate section to deal with. So use A36 steel and assume a connection with one line of 7-8 inch diameter bulk. So single line lang tayo. Okay, so the single line there simply gives us a feel that we are only having one bolt. Okay, so this one bolt per gauge line. Okay, one bolt per gauge line. Okay, member length is 9 inch, 5 feet 9 inches. This is 5.5. We will be using this on the serviceability check. Okay, so we just first steps is to get your AG based on the criteria. Okay, so here's the given load 104.8 obtained from a load combination given. Okay, so this is the load combination LRFD. So 1.2 dead plus 1.6 live is 104.8. We divide it by 0.9 Fy, we get this, and we divide it by 0.75 Fe, we get this. Okay, so this is just an effective area. We cannot compare it to an AG. So we have to convert this to an AG. And we know that for a plate section, automatically your U for plate section U equals 1.0, therefore AE is equal to AN. Okay? So whatever you use, they're just the same. And AG is simply AN plus, of course, the area of the hole. We have one hole with a diameter of 1 inch. Okay, so this is 7/8 volts plus 1/8. Okay, is 1 inch hole. Okay, so if we add this multiplied by a certain thickness to 2.409, which is this one here, we are converting it, we get 2.409 plus T. So we can call this our AG2 and we can call this our AG1. Okay, so we compare AG2 and AG1 by assuming a thickness, let's say T equals 1, to get a value here. So you can start from T equals 1/2 and then checking if it is already reaching a value at least equal to or greater than 3.235 until getting 1 inch course gives us 3.409. So this is your uh, value for AG. Okay, so because we need to round up, no? We need to round up the dimensions of the section. Later, we come up with dividing 3.409 with T, but 3.409 is not a good number in terms of dimension because it has a what a decimal, no? In terms of 0.409, we come up with a rounded width, gross width equivalent to 3 and 3.5. Okay, so we can round this up to 3.5 to have a better width gross of the plate. Okay, so the rounding may be 1 inch or it's up to you how to round it, but this is a very good round of value uh, with regards to plate dimensions. Then we go to serviceability. We check your moment of inertia by getting the moment of inertia of a rectangular section. So this is BT cubed over 12. So B is 3.5, or sorry, B is the width. Okay, so you can call this the width. 1 is the thickness, 12 is a factor, so you get 0.2917. So you are going to use this for the R minimum. So the R minimum is the square root of I all over the area gross, which is 3.5 times 1. Okay, you can multiply that with 1 if you want. So you get 0.2887. So the maximum L over R now is 5.7, the length 75 times 12. So you convert this to inches. So this is converted to inches. Then divided by R, you get 239. So less than 300, so still okay. So this is, you can stop right now here, or you can proceed with the detailing if you want, and the checking requirement if you want on these steps presented. So for the next tension member design, we have an angle bar, I think. Single angle tension bar. The steps are just the same, but here we need to reduce, no? We need to reduce the net area to an effective area because of the shear load. So U is no longer equal to 1. Here, U is equal to 1, okay? Because you only have a plate. So with that, the procedure is still the same. We get the factor load combination, 1.22 dead plus 1.6 live, so you get 80 kips here, or 1.4 dead load, you get 56 kips here. So we have two factored combinations compared to each other. So we choose the greater, so 80 kips. So in the first example, we did not do this because it is obvious that this will always prevail. No? If you have some standard combinations like this. But you can check it if you want. So for step number 2, again, we compute for AG and AE on the basis of the criteria. So this is based again on the LRFD criteria, that TU is equal to 0.9 FYAG and TU is equal to 0.7 FUAE. Okay, so for the AG1, so this is now your AG1, we get 2.47, and for your AG2, we get this from the AE, but since AE is no longer equal to AN, then we have to find the value of U. So U is 0.80, as stated on the recommendation of AISC here on the table. No? So on the table, I I I, uh, I presented on your lecture and also on this uh, presentation. Okay, so single angle. Okay, so U is 0.80. Okay, 4 or more fasteners per line, U equals 0.80 here. Okay, so you just make your table available to you para hindi kayo mahirapan when you are solving the problem. Okay, so divide now your 1.84 to the U there, you get your area net, and the area net will be the basis for your second AG or AG2. So this is now your AG2 coming from AN. Okay, so this is now your AG2. Again, the thickness is not yet known. We have to make use of a trial and error thickness starting from a small value, let's say 1/4, 3/16, 5/8, etc. So here in this problem, what we did is we select thickness from 1/4 to 1/2 until such time that your value of AG2 will be greater than AG1. And in this table, you can see that the AG2 is already greater than AG1 as soon as we started 1/4. So we can assume that AG2 is 2.5 and T is equal to 1/4 inches, and this will control. By the way, we can also check first we can also get your R minimum on the basis of the L over 300 given there, which is 0.6 inches, and then compare this with your R. R on table. Okay? Yung table natin sa angle bar. Okay, so how do we select an angle bar based on AG? So selection process is just trial and error. So we know that your thickness is 1/4 based on that. So a 4 and 3.5 here by 1/4 angle will give you a 2.627. Okay, for as long as you get a 1/4 inch for your thickness, because the formula is based on a 1/4 inch thickness there, you all look into the table where 1/4 inch thick values for your angle is available, and then you get your AG slightly greater. Okay, so this must always be just slightly greater for you to be able to come up with an economical design. Okay, so this is 2.67, 2.5. Again, this was obtained from the table values, and R minimum also from the table values. Compared to 0.60, if these are okay, then you're finished. Okay, so the design, all you need to come up is with the details of the connection, and then you recheck. Okay, so recheck is just recomputing. We compute the P, Tn, and on the basis of yield and fracture. Okay, so that's how to deal with the problems on plates and angles. Okay, I'd like to stop at this point to address your concerns, if any, before we continue solving problem T-8 and some uh, computations on type plates. Thank you very much.